A campus can waste its wiring budget by confusing two different goals: fastest route for one person, or cheapest cable network for everyone. A minimum spanning tree connects everything while deliberately avoiding unnecessary cycles. Every accepted edge should feel like a small proof, not a lucky bargain. By the end, you should be able to reject a route-looking answer, build a cheapest skeleton, and explain why one cheap edge is safe while another cheap edge becomes a cycle trap. Treat this like a campus wiring bill. A route planner asks how one person gets from A to F quickly. A network builder asks how every building receives a connection without paying for redundant cable loops. A spanning structure touches every vertex. Nobody is left isolated. The goal is not to visit one destination, it is to connect the whole set. Kruskal and Prim feel different, but both survive because every accepted edge has a safety argument behind it. A tree connects vertices without cycles. If a cycle exists, at least one edge is redundant for connectivity. The edge count target is n-1, and any extra edge that closes a loop is redundant for connectivity. Think of MST as laying cable for an entire campus. You do not need the fastest walk between every pair of buildings. You need every building connected, with no wasteful loop of cable, at the lowest total cost. MST minimizes the sum of chosen edge weights. It is a network building problem, not a single route navigation problem. The bill counter adds accepted edge weights, not route distance from one source. Here is the emotional bug: a team uses an MST as a route planner, then complains that one delivery path is strangely long. Nothing is wrong with the tree. It optimized infrastructure cost, not every trip inside the infrastructure. Pause on the campus map: are we planning one fastest trip or one cheapest network? Keep the contrast visible: shortest path cares about one traveler from one start to one destination. A spanning tree cares about connecting every location with one cheap skeleton. Those are different questions, so the winning edge can be different. Every accepted edge should feel like a small proof, not a lucky bargain. Both major MST algorithms are greedy. They add edges that are safe, meaning they can belong to some minimum spanning tree. Kruskal and Prim feel different, but both survive because every accepted edge has a safety argument behind it. This is the exact place beginners get tricked: the tree looks like a map, so they expect every path inside it to be shortest. But the tree was never hired to optimize every trip, it was hired to minimize total infrastructure. A cut separates vertices into two sides. Edges crossing the cut are bridges between those sides. Precise rule: the safe edge is the lightest edge crossing a cut that respects the partial tree already built. The cut property works because every connected future must cross the fence somehow. The cut property says the cheapest edge crossing a cut is safe when the cut respects the current forest. In plain language, do not slice through a tree you have already committed to. Kruskal sorts all edges from cheapest to most expensive. It adds the next cheapest edge unless that edge would create a cycle. Kruskal feels like a forest growing everywhere at once, accept a cheap edge only if it connects two different components. Kruskal thinks like a sorted bargain hunter: look at edges from cheapest to most expensive. Take the edge if it connects two different components, reject it if it only creates a loop inside a component already connected. The cycle test prevents waste. If two endpoints are already connected by chosen edges, adding another edge between their components creates a redundant loop. Kruskal and Prim feel different, but both survive because every accepted edge has a safety argument behind it. Before accepting the cheap edge, ask whether it connects new territory or merely closes a loop. Every accepted edge should feel like a small proof, not a lucky bargain. UnionFind keeps track of connected components. It answers: are these endpoints already in the same component? If not, union them. Component labels act like name tags that merge after a successful union. Kruskal begins as many tiny trees, one per vertex. Each safe edge merges two trees until one connected tree remains. Prim starts from one vertex and grows a single connected tree outward, repeatedly adding the cheapest edge leaving the current tree. Prim feels like one tree expanding from a seed, the frontier is the cheapest edge leaving the tree. Imagine two islands are already internally connected. The only question is how cheaply to connect this side to that side. If an edge is the cheapest bridge crossing the boundary, any final network must pay for some crossing, so paying the cheapest one cannot make the answer worse. Prim often uses a priority queue for candidate boundary edges. The frontier idea from shortest paths returns, but the meaning is different. Kruskal and Prim feel different, but both survive because every accepted edge has a safety argument behind it. Kruskal scans edges globally. Prim expands locally from a tree. Both are greedy, and both rely on the same safe edge reasoning. Before accepting the edge, check the component colors. Same color means cycle, different colors means progress. Every accepted edge should feel like a small proof, not a lucky bargain. Unlike Dijkstra, MST is not broken by negative weights. A negative edge is just a very attractive connection, as long as cycles are handled. Let a negative edge lower the bill only when it joins two components instead of closing a loop. A negative edge feels scary because of shortest paths, but here the goal is different, so the intuition must reset. If the graph is disconnected, no spanning tree exists for all vertices. The best you can build is a spanning forest, one tree per component. A spanning tree with V vertices has V-1 edges. More edges would force a cycle, fewer edges would leave something disconnected. Kruskal and Prim feel different, but both survive because every accepted edge has a safety argument behind it. If edge weights tie, there may be multiple minimum spanning trees. The total cost can be the same even when the chosen edges differ. The most common beginner bug is using MST to answer shortest route questions. The result can look plausible because everything is connected, but the promise is wrong. It connects cheaply, it does not optimize every trip. Prim checkpoint: which frontier edge leaves the built tree with the smallest added cable cost? Prim sees the same proof from a different angle. It grows one connected tree outward, always choosing the cheapest edge that leaves the current tree. The cut is the boundary between the grown tree and the rest of the graph. Every accepted edge should feel like a small proof, not a lucky bargain. The proof says, if an optimal tree uses a more expensive crossing edge, swap in the cheaper safe edge. Connectivity remains, cost does not increase. Kruskal pays for sorting edges and Uniqueness checks. Prim pays for frontier updates. The right implementation depends on graph density and storage. Kruskal and Prim feel different, but both survive because every accepted edge has a safety argument behind it. Uniqueness is Kruskal's bookkeeping helper. It answers one question quickly: are these two endpoints already in the same component? If yes, the edge would close a cycle. If no, the edge merges two pieces of the forest. Ask: is the graph connected? Are edge costs meaningful? Do I need infrastructure or routes, and which safe edge process fits the input? Pick the cheapest safe bridge, merge two islands, reject cycle edges, and repeat until every island becomes one connected network. Pause before each cheap edge: does it connect two components, or does it secretly close a cycle? The answer decides whether cheap is allowed. Every accepted edge should feel like a small proof, not a lucky bargain. Pause on the same graph and ask two questions. If one traveler wants A to F, shortest path wins. If the city wants to connect every district with minimum total cable, MST wins. Same edges, different promise, different answer. Use a numeric campus example. The MST may connect A to F through several cheap cable segments, while the fastest A to F route is a different path. That contrast is the whole misconception. Misconception checkpoint: does this tree promise the shortest route between every pair? No, the promise is total connection cost. Every accepted edge should feel like a small proof, not a lucky bargain. To test a candidate safe edge, draw a line that separates the graph into two sides without cutting through a component you already built. Among the edges crossing that line, a lightest one is safe to add. The no-cycle rule is not cosmetic. A cycle means one edge is redundant for connectivity. Removing the most expensive edge on that cycle keeps everyone connected and can only improve the bill. Kruskal needs a fast way to ask whether two endpoints are already connected. Prim needs a fast way to pick the cheapest frontier edge. Same mathematical promise, different working machinery. A minimum spanning tree is the cheapest skeleton that holds the whole graph together. It removes cycle fat but preserves connectivity. By the end, the MST has exactly enough edges to connect all vertices and no extra. That is why the final picture should feel like a skeleton, connected, cheap, and deliberately missing every unnecessary loop. MST connects every vertex with minimum total cost and no cycles. Kruskal grows a forest. Prim grows one tree. The cut property explains why greedy is safe. Next, we will study network flow, where edges have capacities and algorithms search for bottlenecks. Every accepted edge should feel like a small proof,